Hi dear students. So let us continue our discussion along with that question answer section or the exercise section. Okay. So come to the 2.15. The question is that a famous relation in physics relates moving mass m to the rest mass m0. There is a relative motion, it is actually okay, of a particle in terms of its speed v and the speed of light c. Okay. So the relative mass, you have to define the relative mass in terms of v and c, where v is the velocity of the mass and c is the velocity of light. This relation first arises as a consequence of the special relativity due to Albert Einstein. Actually, this relation is the Albert Einstein's special relativity. It is due to the special relativity it is introduced. So a boy recalls the relation almost correctly but forgets where to put the constant c. He writes the equation as m is equal to m0 divided by 1 by v square all raised to 1 by 2. So he forgot to put the value of c in this equation. So by using the dimensional analysis, you have to find out where he has to put the value c. Okay. So here in the dimensional analysis, if we are doing the dimensional analysis, on the left hand side the mass is there, so m will be there. Okay. Right hand side, on the numerator again m0, so the dimensional formula for m0 will also be m. Okay. You know that as per the dimensional analysis, for an equation both left hand side and right hand side should have the same dimensional formula, isn't it? So here on the left hand side m is there, but on right hand side if you are seeing there denominator a v square is there, that is a v square all raised to 1 by 2, that we can say the dimension of v will be there, l by t will be there, so we have to cancel that one. Okay. So that means the c is the velocity of light, isn't it? Okay. C is the velocity of light and both v and c are having same dimension. V is the velocity of the mass of whatever the body. Okay. Body, and v is the velocity of the body and c is the velocity of light. So if we are writing the equation like this, m is equal to m0 divided by 1 minus v square by c square all raised to 1 by 2, where the v and the c are having all same dimension, so that will cancel each other. And afterwards on the left hand side the m will be there. Okay. As well on right hand side also the m will be there due to the mass m0. So this will be the correct equation. Okay. So you have to do the dimensional analysis over here. Okay, now let us come to the next question, that is 2.16. The unit of length convenient on the atomic scale is known as the Armstrong and is denoted by, okay, the Armstrong it is denoting like this. Okay. So you know that the atomic size is very small. Actually that is up to 10 to the power minus 10 meter. Okay, that is the power or range. So it will be actually the 1 Armstrong is actually 10 to the power minus 10 meter. Okay, 10 to the power minus 10 meter. The size of the hydrogen atom is about 0.5 Angstrom. Okay, size of the hydrogen atom is about 0.5 Angstrom. So what is the total atomic volume in meter cube? The size of the hydrogen atom is given. Okay, that means the radius of the hydrogen atom is 0.5 Angstrom. So you have to find out the volume of one hydrogen atom, and afterwards you have to find the volume of the 1 mole of hydrogen atom. 1 mole means the number of atoms will be there 6.023 into 10 to the power 23 atoms will be there, isn't it? Avogadro's number in 1 mole atom. Okay, first of all we have to find out the volume of the one hydrogen atom. As you know, the atomic radius of hydrogen atom is 0.5 angstrom, that is 0.5 into 10 to the power minus 10 meter. Then we know that the atom is in a spherical shape. For the sphere, the volume, equation for volume, it is V is equal to 4 by 3 pi into r cube. So you have to substitute the value 4 by 3. Okay, forgot to put the 3. Okay, 4 by 3 into pi into r cube. Then you will get the answer as 5.233 into 10 to the power minus 31 meter cube. You just do that calculations. Okay, then you will get an idea. So the volume of one hydrogen atom, it is 5.233 into 10 to the power minus 31 meter cube. Okay, now you have to find out the volume of hydrogen atom in 1 mole of atom. In 1 mole of atom there will be 6.023 into 10 to the power 23 number of individual atoms will be there. So you have to multiply this 6.023 into 10 to the power 23 along with the volume of one atom. Then you will get the total volume of 1 mole of atoms. Okay, so 5.233 into 10 to the power minus 31 into 6.023 into 10 to the power 23. So the answer will be 3.152 into 10 to the power minus 7 meter cube. Okay, 3.152 into 10 to the power minus 7 meter cube will be the volume of 1 mole of hydrogen atom. Is it clear? Okay, now let us come to the next question, that is (2.17). 1 mole of an ideal gas at standard temperature and pressure occupies 22.4 liter. This is the molar volume. Okay, so 1 mole of an ideal gas at standard temperature and STP, okay, standard temperature and pressure, occupies the volume as 22.4 liter. So what is the ratio of molar volume to the atomic volume of a mole of hydrogen? Okay, 1 mole of hydrogen. Okay, so and one more question is there, why is the ratio is so large? So here the molar volume you have to find out. Sorry, the molar volume of 1 mole of gas, it is already given, that is 22.4 liter. This 22.4 liter is actually 22.4 into 10 to the power minus 3 meter cube. That is 1 meter cube is actually 1000 liter. You have to remember that one. Now the volume of 1 mole of gas is actually, you know that the volume of 1 mole atom into Avogadro's number. Here also we are considering the same hydrogen atom, so you have already find out that answer, the volume of 1 mole of hydrogen atom in the previous exercise, isn't it? 2.16, you have already found that one. So that is 3.152 into 10 to the power minus 7 meter cube. Okay, that is the molar volume of hydrogen atom. Now we have to take the ratio of molar volume divided by volume of 1 mole atom. So molar volume, it is 22.4 liter. That means 22.4 into 10 to the power minus 3 meter cube, and divided by the volume of 1 mole of atom, that is you have already found that one as 3.152 into 10 to the power minus 7 meter cube, and you have to take the ratio, and it will be 7.1 into 10 to the power 4. Okay, 7.1 into 10 to the power 4. Here you can see the ratio is very high. Actually, the interatomic separation in the gas is very large as compared to size of the hydrogen molecule. If you are considering the molar volume is actually considering a large area. Okay, so you can see there will be an interatomic distances will be the each molecule. Okay, or each atom, in between each atom there will be some more separation will also be there. So included that separation, the molar volume is very large as compared to the atomic or molecular weight of the hydrogen volume of the hydrogen molecule. That is why this ratio is becoming very huge. Okay, is it clear? Okay, now let us come to the next question, that is 2.18. Explain this common observation clearly. If you look out of the window of a fast moving train, the nearby trees, house, etc. seems to move rapidly in direction opposite to the train's motion, but distant objects, hilltop, the moon, the star, etc. seems to be stationary. Okay, so what's the reason behind that one? The near objects will be moving faster in the opposite direction of the train, but the distant objects will be remaining stationary. The question is asked to find out the reason. Okay, so can you guess that one? What will be the appropriate reason for that one? Actually, in the case of the closed object, or means near objects, okay, closer objects or near objects, you know that the angle of view, okay, whenever we are changing the position from one point to the another point, the angular displacement will be more. Okay, the angular displacement will be more. We have already discussed those things in the theory class. But for a distant object, if you are moving the same distance, okay, but the angular displacement will be very less. Okay, a negligible angular displacement will be happening for the distant objects. So that is the reason why the near objects will move faster and the distant objects will remain or seems to remain as stationary. You have to mention the term angular displacement over there in that question. Okay, the angular displacement in the case of the nearer object, it will be more for a displacement of d. For the same displacement of d, the angular displacement for the distant object will be very small. That is why the distant object will remain or seems to remain as stationary, but at that time the nearer objects are moving fastly. Okay, is it clear? Now come to the next question, that is 2.19. The principle of parallax in section 2.31 is used to determine or determination of the distance of very distant stars. The baseline AB is the line joining the Earth's two locations 6 months apart in its orbit around the Sun. So AB is actually joining the distant or the path which is moved by the Earth by 6 months. That means from one point to the opposite point, half of its path of the entire orbit. So AB will be actually the diameter of that orbit, isn't it? Actually, if the Sun is starting from A and if it reaching in A, that means 12 months should be needed. Now we are considering the distance for the movement of 6 months only, or for the motion of the 6 months. That means A to the exact opposite of that day, that means B. Okay, So the distance, direct distance a to b will be the diameter of that circular path or orbital path. Okay. So that is the baseline is about the diameter of Earth's orbit. The value it is 3 into 10 to the power 11 meter. So the b value, okay, the a to b, it is given as small b, and which will be is equal to 3 into 10 to the power 11 meter. However, even the nearest star are so distant that with such a long baseline they show parallax only of the order 1 second. Okay, 1 second means arc second. So the value of theta is 1 second. Okay, 1 second is the angle of value of theta. Now the definition of parsec is given. A parsec is a convenient unit of length on the astronomical scale. It is the distance of the object that will show a parallax of 1 arc per second, or 1 second of arc from opposite end of the baselines, equal to the distance from Earth to Sun. So if the distance of view, it is equal to the distance of the Earth to Sun, okay, and if the angle is making angle of vision, if it is angle of arc distance, if it is 1 second, then the distance between the observer and the star will be considered as 1 parsec. Okay, that will be 1 parsec. So you have to consider the position of the observers as one at a sun, at the position of sun, and another one at the orbit, maybe on A or B, and the theta value should be taken as 1 second. Then only you can find out the d as a in terms of parsec. Okay, 1 parsec. Now the real question is that how much is a parsec in terms of meters? Okay, how much is the parsec in terms of meter? Here the d value is actually 1 parsec. So if you are finding the d value in meters, then you can obtain the value of parsec in meter. Now the basis is b is small b is actually 3 into 10 to the power 11. So the distance between star and Earth is taken as capital D. Okay, and theta dash is the combined angle that is from A to B. If you are combining the observing lines, okay, from A to B, from A and B, if you are combining, the angle will be theta dash. But here we are considering the one of the observer. The observer is standing from sun, or observing from sun, and from one point, maybe A or B. So the angle will become 1 second, and it is theta. Okay, theta will be is equal to 1 second. We know that 2 theta dash is actually b by d. Okay, 2 theta dash is equal to 2 theta is equal to b by d. That means theta dash is equal to b by d. So d will be is equal to b by theta dash into 2. Okay, b will be is equal to d will be is equal to b by theta dash into 2. Are you getting or not? Actually the theta dash is the angle if the observing point's distance is equal to small b. But we know that we have to find the d in terms of parsec. Parsec is the distance between the observer and the particle, maybe a star, consider as the star. If the baseline value means from wherever the observer is looking, that point's distance should be is equal to the distance between sun and Earth. So we are given with the value of theta dash. but you have to convert that in terms of theta, and then you have to find out the value of d. Then only d will be is equal to 1 parsec. So instead of taking the sun, we are approximately taking the distance or the theta angle. Theta is the angle between C and A. Okay, C is the center. Okay, so that means we are equally dividing the theta dash into 2, that is 2 theta values will be there, and theta dash will be is equal to 2 theta. So theta dash will be in terms of theta, as we are using the parallax method, so theta dash will be is equal to b by d. Okay, theta dash will be is equal to b by d. B by d. That means 2 theta will be is equal to b by d. Okay, one correction is there. 2 theta will be is equal to b by d. Okay, now d will be is equal to b by theta into 2. B by theta into 2. Theta dash will not be there. Okay, now you have to substitute the values, and you have to remember that 1 second you cannot use that one over there. Okay, 1 second you cannot use. Instead of that one, you have to convert that into the form of radians. So 1 second will be is equal to 4.85 into 10 to the power minus 6 radians. So d will be is equal to b you know that 3 into 10 to the power 11 meter. 3 into 10 to the power 11 divided by the theta value, it is 1 second, and you have to find the value in theta dash, because the angle between A and B, it is theta dash actually, isn't it? So 2 into theta will become, so that means 2 into 4.85 into 10 to the power minus 6. 4.85 into 10 to the power minus 6 is actually 1 second, isn't it? In radians it is 4.85 into 10 to the power minus 6. So the answer you will obtain as 0.3092 into 10 to the power 17. Okay, that is the value of capital D, and it is 1 parsec. Okay, it is 1 parsec. Now that means 1 parsec is 3.09 into 10 to the power 16 meter. So 1 pc is equal to 3.09 into 10 to the power 16 meters. So we have found the value of parsec in meter. Okay, I think you understood this one. You just read that portion, that parallax method, that portion you just read, then you will understand thoroughly. Okay, now we can go to the next question. That is 2.20. The question is that the nearest star to our solar system is 4.29 light years away. How much is the distance in terms of parsec? Okay, how much is the distance in terms of parsec? So you have to convert that light years value in the term of parsec. And how much parallax would this star named Alpha Centauri show when viewed from 2 locations of the Earth 6 months apart in its orbit around the Sun? Okay, that baseline value, the same value should be taken over there. Okay, in the previous question, whatever the value you have taken for that B, that same value will be here also. Anyway, now first of all we have to convert the value into the light year value, 4.29 light year value in the terms of parsec. You know that 1 light year is actually 9.46 into 10 to the power 15 meter. Okay, then 4.29 light year will be, we have to multiply the value 4.29 with the 9.46 into 10 to the power 15 meter, and you will obtain the light year, 4.29 light year in terms of meter as 4.58 into 10 to the power 16 meter. Okay, we have already found that 1 parsec is 3.08 into 10 to the power 16 meter. Okay, so both the light year and the parsec values have converted into meter. Now if you want to find out the value of 4.29 light year in terms of parsec, you can divide 4.58 3.58 into 10 to the power 16 meter divided by 3.08 into 10 to the power 16 meter. Okay, that means you are converting that light year in terms of parsec. Okay, both, first of all you have converted both into the terms of meter, then only we can cancel do the calculation. And then you are dividing 4.58 into 10 to the power 16 meter divided by 3.08 into 10 to the power 16 meter. That is 3.08 into 10 to the power 16 meter is actually 1 parsec. Okay, then you will obtain the value as 1.32. That is the 4.29 light years. 4.29 light years will be is equal to 1.32 parsec. Okay, now you have to convert the parsec into parallax. Actually 1 parsec means 2 second parallax. Parallax is the unit over there. So 1 parsec is 2 second parallax. So 1.32 parallax will be, you have to remember this one, this relation. Okay, 1 parsec is 2 second parallax. So as you have to convert the parsec value into parallax, you have to multiply that with the 2 seconds. So 1.32 parsec will be 1.32 into 2 seconds, that will be 2.64 seconds. That will be the final answer. So here both three relations you should remember. One light year is equal to 9.46 into 10 to the power 15 meter. Then 1 parsec, we have derived this one in the previous question. Okay, so 1 parsec is equal to 3.08 into 10 to the power 16 meter. That one also you have to do remember as well. One more thing, that is 1 parsec is actually 2 second parallax. Okay, these are the three major equations that you have to remember and you have to study. Okay, in another questions also you can use this relation. Now let us come to the next question, that is the 2.23. okay, 2.21 and 2.2 we will discuss later. Now let us come to the 2.23. okay, the question is that the sun is a hot plasma ionized matter. Plasma means ionized matter. Okay, with its inner core at a temperature exceeding 10 to the power 7 Kelvin and its outer surface at a temperature of about 6000 Kelvin. At this high temperature no substance remain in a solid or liquid phase. In what range do you accept the mass density of sun to be, mass to the density ratio, mass density of the sun to be in the range of densities of solid and liquid or gases? Check if your guess is correct from the following data. Okay, we have to find out the density of sun now. Okay, so the mass and the radius of sun is given. Actually you know that density is actually mass by volume. The sun is considered as a sphere, so the volume of the sphere will be 4 by 3 pi r cube, where r value is given as 7.0 into 10 to the power 8 meter and the mass m is equal to 2.0 into 10 raised to 30 kilogram. You have to just substitute the values and you can find out the density of the sun. The question is simply asking to find out the density of the sun. Okay, the temperature values are given. Actually by giving such data, they are just complicating the concept. They are just trying to confusing you. Okay, the data that we needed is actually the mass of the sun and the radius of the sun. Okay, so we are just substituting the values. So m, it is equal to 2.0 into 10 to the power 30 kilogram divided by 4 by 3 pi r cube. Pi it is 3.14. okay, and the r value it is 7 into 10 raised to 8 meter. It is given r cube, so 7 into 10 raised to 8 meter cube. So the final value you will obtain as 1.4 into 10 raised to 3 kilogram meter raised to minus 3. Okay, so this will be the density of the sun. Okay, so you just do the calculations. Okay, do the calculations and check whether it is right or wrong. Now let us come to the next question, that is the 2.24. 2.24. 2.24. The question is that when the planet Jupiter is at a distance of 824.7 million kilometers from the Earth, its angular diameter is measured to be 35.72 seconds of arc. Calculate the diameter of the Jupiter. So the angular diameter is measured and the distance is also given. So theta value is there and the capital D value is also given. So the small d value will be the diameter of the Jupiter. Okay. So you know that theta will be is equal to small d by d. So small d will be is equal to theta into d. So here theta is given as 35.72 seconds. You have to convert that one into radians. So it will be 35.72 into 4.885 into 10 raised to minus 6. And the capital D value it is given as 824.7 million kilometers. Okay. 824.7 million kilometers, that is 824.7 into 10 raised to 6 kilometers. So just multiplying both these values we can obtain the small d value as 1.429 into 10 raised to 5 kilometer. Okay. So is this much clear? So we can wind up the class or this section by here. Okay. So you just go through the textbook and just check the answers once again. Okay. And as well you just try to you should write these question answers in your notebook. Okay. Okay then. Wish you have a nice day. Thank you.